we're going to prove the binomial theorem. A plus b to the n is equal to, put it here, equals to n choose 0, n choose 0, a to the n plus n choose 1, a to the n minus 1b, plus n choose 2, a to the n minus 2b squared, all the way down to n choose n minus 1, which will be a, b to the n minus 1, plus n choose n, b to the n. For any integer n. For any n in the positive integers. Well, to me, this clearly looks like an induction proof. So let's start with n equals 1. The left side is going to be a plus b to the 1, which is just a plus b. Now, does it equal to the right side? Well, n is just 1. Okay, so we're going to get 1 choose 0 times a to the 1. Let's write that down neatly. We're going to get this, where n is 1. We're going to get 1 choose 0 times a to the 1 plus, 1 choose 0 plus 1 choose 1 a to the 0, because n minus 1 is 0, times b. Okay, that's 1, that's a, plus, that's 1. You don't even have to write down the a to the 0, because when the top and the bottom are the same, you just get b to the 1. So this is b to the 1, and 1 choose 1 is 1, times b to the 1. Well, this is a, plus, that's b, and it checked. Let's try it for another n, for good measures. N is 2. Well, a plus b to the 2, why, that's a squared plus 2ab plus b squared. Does it equal to, now I use the formula. The formula is 2 choose 0 times a plus 2 choose 1, sorry, a squared. And then ab plus 2 choose 2 of our b squared. Well, 2 choose 0 is 1 times a squared. 2 choose 1 is 2 times ab. And 2 choose 2 is 1 times b squared. So here, 1 times a squared, 2ab, 1 times b squared is b squared. So here we did get the same answer. So now let's assume the next step. Assume for n equals to k, the following is true. That a plus b to the k is equal to k choose 1. I meant to say k choose 0. A to the k will b's plus k choose 1. A to the k minus 1b, all the way down to k choose k minus 1, which will be a, b to the k minus 1, plus k choose k, b to the k. So we're going to assume that this equal sign is valid. We're going to assume that. Now, we must show for the next n, that is k plus 1, we must show that a plus b to the k plus 1, this is equal to k plus 1 choose 0, a to the k plus 1 plus k plus 1 choose 1, which is a to the k times b, all the way down to k plus 1 choose k. Let's get that plus 1 in there. K plus 1 choose k, and we're supposed to get a b to the k plus k plus 1 choose k plus 1 times b to the k plus 1. And we do not know if that's true, and we can't assume it's true, but we have to show it. Okay. So I'm going to start with the right hand side, and I am going to show that it equals to a plus b raised to the k plus 1. But first, we need to prove some theorem. I'll call it a lemma because, actually, I'm just going to prove it by words. Suppose your goal is to choose R objects from N objects. That is your goal. And say we numbers are N objects. 1, 2, 3, 4, N minus 1, and N. Now, I'm going to partition the number of ways of choosing the R objects from 1 into 2 disjoint partitions. One where we do pick the nth member, and the other time we do not pick the nth member. Well, if I do pick the nth one, then my goal was to pick R. But so now I only have to pick R minus 1 because I picked the nth one. And I get to pick it from n minus 1. Now, if I'm not going to choose the nth one, then I still have to choose my R objects, because I didn't choose any, and I have to choose them not from n anymore, but from n minus 1. And there is a combinatoric argument why this is equal to that. And we are going to use that. Now, just to say it somewhat in words, you have n choose R, and when it comes to the top part, the n's go down by 1. Always, in both cases. And the bottom number, one of them stays R, and the other one becomes 1 lower. In fact, just so it looks like what I have above, one of them stays R, and the other one becomes 1 less. Okay, the tops, they go down 1 and they're the same, and the bottom, they stay the same or they go down 1. But more importantly, it's valid because of the argument which I just gave. Alright, so now, like I said, we're going to start with this. Okay, so k plus 1 choose 0 times a to the k plus 1 plus k plus 1 choose 1 times a to the k times b, all the way down to k plus 1 choose k times ab to the k plus k plus 1 choose k plus 1 b to the k plus 1. Now, we are going to rewrite. So this one I'm not going to mess with. This is 1 times a to the k plus 1. That is just a to the k plus 1. But this one, I'm going to play games with. I'm going to write the combinatoric part as a sum. I make the k plus 1 one less in both of them, and I keep the choose the same and one less. The reason I didn't do that with this one is 1 less than 0 is negative, and I don't want to deal with negative numbers. Times AK times B plus, now I break this one up into a sum, the combination. I make the top one less, and in one case the bottom stays the same, and in the other case it becomes one less, times, oops, close the bracket, times AB to the K, plus, I do not want to do it to this one, and the reason is, if I'm supposed to have a sum, I make the top one less, and then I keep the bottom the same, and I make it one less. Wow, you can't choose k plus 1 objects from k objects. So I'm just going to leave it as B. So k choose 1, choose k plus 1, choose k plus 1 is 1, times b to the k plus 1 is just b to the k plus 1. So these two, we're going to just live with them for right now. So you get ak plus 1. Now when I add these, first I want to add the first ones. So I get k choose 1, ak to the b times b, plus I'll have k choose 2, ak minus 1 b squared, all the way down to k choose k, ab to the k. We have that one. Plus, now I'll add on the second ones. We have k choose 0, ak to the times b, a to the k times b, plus k choose 1, a to the k minus 1 b squared, all the way down to this one here, plus k choose k minus 1, ab to the k, plus, don't forget, b to the k plus 1. Okay. This is called alphabet soup. So this is equal to a to the k plus 1 plus, now in here I'm going to factor out an a. So I'm going to have k choose 1, k choose 1, a to the k minus 1 times b, plus k choose 2, 1 less on the a to the k minus 2 times b squared, all the way down to k choose k. I brought that a in front, so just b to the k, plus this piece. And in this piece, I'm going to factor out a b. I have b times k choose 0, a to the k. This piece right here would be factored out. Plus this, k choose 1, a to the k minus 1 times b. I factored out one of the b's. All the way down to this term, where I will have k choose k minus 1, ab to the k minus 1. And don't forget to add the b raised to their k plus 1. Now, the reason I factored out the a's and the b's is so this starts looking like the binomial theorem. The only problem is that we're missing that k choose 0 term. So this is a. I'm going to hold off on this for a second. This is a times. Now, I'm going to write this in here. K choose 0 is 1. K choose 0 is 1 times a to the k. Why a to the k? Because I factored out one of these k's. Plus k choose 2. Plus k choose 1. A to the k minus 1b. All the way down to k choose k, b to the k. Now that's the binomial theorem. Plus b times all of this, k choose 0, a to the k, plus k choose 1, a to the k minus 1, times b, all the way down to k choose k minus 1, ab, k minus 1. Now, I would love to have k choose k times b to the k. Now, k choose k is 1. K choose k is 1. Oops. So, I'm really only adding inside the brackets b to the k. Because 1 times b to the k is b to the k. But then, that b to the k right here is multiplied by the b in front, so I'm really adding b to the k plus 1 out of nowhere. Well, not really. I'm supposed to be adding b to the k plus 1. Alright, so now we're almost done. This is equal to a times, now what's in the brackets is simply a plus b to the k plus b times what's in the brackets, well, that's a plus b to the k. So here I have a plus b to the k's, and I'm adding on b, a plus b to the k's. So in all, I'm going to have a plus b to the k. And this is understood to be 1, and basic math tells us in multiplication, we are multiplying. If the bases are the same, and they are, just add the exponents. 1 plus k is the same as k plus 1. But that's exactly what I wanted to show. I wanted to show that this really equaled to this. Okay? I started off with this. I know I did, because here it is right here. I started off with this equation right here, and I just showed that it equals to a plus b to the k plus 1. Theorem is proved. You no longer have to think, well, is this true? Now, I'll sneak in another nice theorem. If you have, say, 1 plus 1 to the n, well, say a and b are just 1. So you're going to get, n choose 0, 1 to some power, 1 to the n, times 1 to the n minus 1. Both of those are 1s. Plus n choose 1, 1 to the, oh, this should not even be here. I apologize. 1 to the n. So maybe we'll move this over. It doesn't want to be moved alone. Okay, so plus, I don't want to do it in blue for some reason. N choose 1, 1 to the n minus 1 times 1, all the way down to our n choose n minus 1, 1 times 1 to the n minus 1, plus n choose n, and you get 1 to the n. But that's just n choose 0. because multiplying by 1 doesn't do anything, plus n choose 1, multiplying by those 1s don't do anything, plus n choose 2, plus n choose 3, all the way up to n choose n. And 1 plus 1 is 2. So 2 to the n equals this in any row. Oh, these are the entries of the Pascal triangle. Any row in the Pascal triangle adds up to 2 to the n. And more importantly, if you have a subset of size n, if you have a set of size n, and you want subsets, well, from those n you can pick 0, or you can make subsets of 0 and choose 0 ways. You can make subsets of size 1 and choose 1 ways. You can make subsets of size 2 and choose 2 ways. And you can make subsets of size n 1 way, namely, and choose n ways. And that's going to equal to 2 raised to the number of elements in the set. So that's why the number of subsets in a set is 2 to the n. And this completes the proof of the binomial theorem. If you have any comments about the way I did the proof, or you know of a better proof, or you want to see another proof of some other theorem, let me know. I'll work on it. Watch and learn.